it's a very special day because we are celebrating the 100 of these game changer seminars. And it's a very special occasion. These seminars have been absolutely fantastically successful. And we are now celebrating number 100. They've covered a variety of topics, exactly reflecting ISSI, rich portfolio of activities, from earth science to cosmology to solar and plasma. I mean, just to give you some numbers about the impact of these seminars, we had 14,640 attendees throughout the 100 seminars, and they've been viewed 70,000 times on YouTube. And so to celebrate this very special occasion, it was most appropriate to invite the person who actually had the brilliant idea to start this series. The series, Tilman Spohn, very well known to ISSI, previous executive director. Tilman started this series in 2020, exactly during the pandemic. And for all the people who are following online, you know that ISSI's strength is to have people meeting here in person. And the pandemic was an extremely hard hit because suddenly the core mission could not be done. And so Tilman had the very, very brilliant idea to create this tool to connect the community, to keep the community engaged. They couldn't come here in person, but they could still continue the conversation, the scientific conversation. They could still continue advancing science like ISSI does and has done for many years. So I think that we are celebrating today a series, which, by the way, I think it has the best name ever. And it has been really, the quality of these seminars has been faithful to the name. Extremely compelling topics, extremely engaging speakers. And so we welcome today, as the speaker of the 100 Game Changer Seminar, Tilman Spohn. As I said, Tilman is very well known to ISSI. He was director of the DLR Planetary Research in Berlin from 2004 to 2017. And then he was executive director here at ISSI throughout 2022. Tilman is a world expert of thermal and tectonic evolution of Earth, terrestrial planets, small bodies in the solar system, and numerous publications. And just last week, he held a very interesting workshop here at ISSI on the geophysics of exoplanets, and basically how studies of Earth can inform the search of life in the universe. And this is the title of the seminar that he will give today. So I thank you all for attending. I will give the floor to Tilman now. If you have any question, as it is are used, just put them in the chat, and we will answer them at the end. But let's have Tilman telling us how studies on Earth can inform the search for life in the universe. Thank you, Tilman, for being with us today.
Thank you very much, Antonella. It's a great pleasure and honor to be invited to give this 100th seminar. And I'm not sure we thought about this when we started the series. Oops. Actually, I wanted to go up. Yeah. In May 2020, and Antonella has already told you about the number of attendees and so forth, but maybe it's just a quick look back at that. In the first years, we looked at missions that changed the game, and that's actually where that name of the seminar came from, in solar system astrophysics and earth sciences. And after it was quite successful, we thought that we continue as the pandemic did continue, but we changed gears a bit and had seminars on ideas and findings about the solar system, the universe, and our terrestrial environment, then habitability, from galactic to microbial scales, viewing Earth from space, captivating cosmology. And I think that's a highlight because in that period, we had two Nobel Prize winners actually with us, Adam Rees and Reinhard Genzel. And then space weather, and then later, since the spring of 2023, I think they changed it to a monthly cadence, just to, as we're back at ISSI, I mean, this is a very wise move, I think. And we have 99 seminars today, and I'm really proud and very honored, to give this 100th seminar. And I want to speak about the geophysics of exoplanets and give an example of how studies of the Earth can inform the search for life in the universe. Of course, there are many examples, but I want to talk about an aspect of this that is related to my personal research. But I should also say that, as Antonella has already mentioned, that 2 weeks ago we had a workshop at ISSI bringing Earth scientists, astronomers, astrobiologists, plasma physicists, and planetary scientists together, many of whom met for the first time. And that was about the geoscience of exoplanets. You see that I have narrowed the subject of this talk a little bit to geophysics. Geoscience is, of course, broader. And the idea was to, develop concepts that would go beyond the concept of habitability that is based on the availability of water. And during that workshop, we developed, we exchanged ideas and we developed criteria, how we would go ahead. But what are we talking about? This is a cartoon of the exoplanet population, and we're now counting about 5,600 or so exoplanet detections that are confirmed. But there are many more, waiting to be confirmed, 7,000 something. I also saw the number of 9,000, the one that I can confirm from the NASA Exoplanet Archive is a little smaller. And of those confirmed planets, about 1,600 have radii that are a little smaller than the Earth, about Mars size, to about 2 Earth radii, or masses between, if you take the power of this factors here, from 1/10 of the Earth mass to about 10 Earth masses. And this is what we call, what we think is the family of the rocky planets that make about 40 or something percent of the planets that we have detected. And these, were the subject of that seminar, of that workshop, and also the subject of this seminar here. Now you can see that the rocky planets, take this area here, the detected rocky planets, of up to 2 or so Earth radii. And here is the frontier of observation, where actually, detections have been made. And it is, of course, interesting to see how the planets in the solar system would fit in here. And I've done that. And you see that Venus and Earth are actually, in above that frontier, while Mercury and Mars are, still away from to be detected, but that will change in the future, as most of you may already know, with missions like Plato and so forth. Now, why would exoplanetary scientists be interested in the Earth, and vice versa? Why would geoscientists be interested in exoplanets? Well, for the exoplanetary scientist, I think we can say that, of course, Earth is a reference planet. It's the best known and studied planet that we have, and therefore naturally serves as a reference as we search for other inhabited worlds. But the Earth, and we have records of that, has been many different worlds in the past that we may see or may expect to see on exoplanets. So magma ocean planet, for instance, something that the Earth went through in its early evolution, stagnant squishy lid planet, plate tectonics, a hot greenhouse, snowball planet, an oxic world, and so forth. So, for all of these worlds, we have records in the geological record that, can be used and to better understand what we're observing or will be observing or expect to be observing on planets from other worlds. But why would the geoscientists be interested in exoplanets? Well, comparative planetology is the name of the game. And coming from geophysics and from the earth sciences, I can say that for us earth scientists, it's always good to compare. So Mars is interesting as well as Venus, as well as Mercury, as for the rocky planets, all the ice moons or the Jovian moon Io, with which I have spent part time of my career. But now that we have planets beyond this and a larger number of planets to be studied, we may be even hoping that one of these days we can do some statistical studies on planetary properties. And that is, of course, something that the astrophysicists have, but for us, in the planetary community, planets at the moment are individuals. And to be able to study in a more statistical sense, we need larger numbers. And therefore, we are very much interested in the discoveries of these planets and how they would look like. And in addition to that, if we actually found an independent abiogenesis, then that would, of course, be of tremendous importance and would advance our understanding of the origin of life. Now, this is timely. I've here at the side, I have the cover of an issue of Elements of Geoscience Beyond the Solar System. But it has never been the theme of an ISSI workshop, and we expect to publish a series of papers and an ISSI book on that, and that we hope, of course, will serve as a reference for these studies. Now, let's look at the Earth a little bit, just a brief summary of what this plan is all about. I like this cartoon of from Lagos that Annie Kaznav gave me some time back when I was at ISSI. It is the biggest rocky planet in the solar system, slightly bigger than Venus, but the biggest. The interior pressure is 360 GPa, but that is actually small in comparison to the pressure that we would find at the center of some of these super Earths of two Earth radii, for instance. And that is important because, in the laboratory, we cannot even reach these pressures here. So much of the pressure range that we are modeling in big exoplanets, and I'm talking about super Earths of two Earth radii, not more, is beyond the range of what we can study in the laboratory and do understand from theoretical studies. So that is to a large extent terra incognita. Now, the compression is up to 30%. There is an iron core. We expect many exoplanets to have iron cores. And there is an adiabatic temperature range, so the mantle is important for convection of about 1,000 degrees. We have an hydrosphere and an atmosphere, important, of course, if we talk about life on other planets. We have active plate tectonics, and this will be, part of the story that I'm going to tell you today. We have magnetic field that is debated to be important for protecting life against radiation, but atmospheres also protect, and how exactly that works is still a matter of debate and has been a matter of debate during our workshop. And then finally, of course, we have life, and we have feedbacks to atmosphere and surface, and probably interior processes through biologically enhanced weathering and biogeochemical cycles, which are of importance and of interest in discussing the Earth and other planets. Now, why do we think that it might work, to translate, so to speak, the Earth onto these rocky planets? And part of the motivation comes from these studies here. Here is the magnesium to silicate ratio and the iron to magnesium ratio of a large number of stars in the solar neighborhood collected by Natalie Nickel in the Hypatia catalog. And here is a collection of solar twins. And Putirka et al. Calculated mineralogies, from these compositions. And as you can see, the mineralogies extend beyond what we have on Earth and the terrestrial planets, from orthopyroxene to olivine. But they cover basically although extending it, the same range of compositions and mineralogies. And therefore, we can hope that what we learn from the Earth and the terrestrial planets, Mars and others are in here as well, would work on these rocky exoplanets as well. So the processes should be similar, and that is one of our basic assumptions that we do. In addition to that, here we have a mass radius plot of rocky planets with well-known masses and radii, smaller than 25% and 8%. There are many more known, but this is a very good data set. And you see that, this is a relatively small number of only about 10 planets or so. But they are plotting onto a theoretical curve that would characterize rocky planets. So that is another, indication of that these rocky planets, orbiting other worlds, would follow the same physics and have similar compositions and mineralogies to what we are, used to have in the solar system. Now, when we talk about life, then of course, and I was saying that we were trying to get beyond the habitability concept, we would, of course, be talking about the habitable zone. And that is a zone of distance from the star where temperatures are such that within a given atmosphere, you would expect temperatures to be such that water would be fluid. And this is, of course, based on the notion that life as we know it needs water. And that is the most basic matter that, or element, or molecule, that you would, like to have if talking about a planet that could support life. What you see here is, of course, G-stars and Earth and Mars in the solar system, Venus outside the habitable zone, and many more, like 20 or so, plotted here of exoplanets. But these are basically around M-stars, so we haven't really seen second Earths or habitable planets around a similar star to what we have in the solar system. Anyway, we're counting about 70 planets that are in the habitable zone, of which one is Mars-sized, and about 30 are about Earth-sized. All of them are orbiting M-stars, just to say. About 40 super-Earth mini-Neptunes, some of which do orbit G-stars, but most of them M-stars also. A total of 70 that are counted in the Habitable Worlds catalog that you can visit on the web. And of course, this is basically due to the fact that what we can observe today is relatively close to to the host star of the planets under consideration. And that will, of course, be extended by Plato, a mission that is coming comparatively soon on the timescales of ESA and other missions. And that we can expect to widen our field and also get us habitable planets orbiting G-stars and others. So the distance range, from the central star is something that Plato should serve us. Now, what is the rationale for considering other criteria than water as a concept for habitability? And this is, the notion that we have about 7D at the moment. And if you would have to do costly follow-up observations, then we may be getting into numbers where that we just prove to be too unspecific for costly, at least, follow-up observations. And therefore, one is motivated to look a little closer and see what else would we need in order to support life, and can we develop criteria for habitability that go beyond just the availability of water. But one should, of course, be aware that as we, as we get more specific, we increase bias, of course, because we're looking then for life that is closer to what we know from Earth as we do so. But still, I mean, this is something that makes sense to do. And more specific planetary properties would, for instance, include the availability of basic nutrients, such as the elements phosphorus and nitrogen. Also, the potential for the buildup of free oxygen to support more advanced life forms as we have on Earth, or the presence of a magnetic field. And if you consider these three bullets, for instance, you find yourself pretty soon into a discussion of the planet, as a complex system and as an engine. So we're looking at atmosphere and hydrosphere. You would look at the interior and magnetic field evolution. You would look at star-planet interactions, possibly look at tides and how they would influence the rotation rate or act as a heating mechanism for the interior. You would look at tectonic modes. Is plate tectonics important? And that is what I'm going to address further in my talk, you would look at land surface distributions. Why land surface distributions? Well, the Earth biomass, and taking again the Earth as an example, is not equally distributed. Rather, we find that most of the biomass is to be found on land, on the continents. This is 470 gigatons of carbon. Not all of that is contributing to photosynthesis at the moment, because this includes trees, tree trunks, and so forth. But still, you have this number here in comparison to about 6 gigatons of carbon in the marine world, or 70 gigatons in the deep subsurface, the second largest. And you see that, large areas of the oceans are in fact deserts, similar to deserts on land. And you have, areas that are nutrition limited, while on land you have areas that are water limited. Also, if you look at consumers and producers, you see that on land, I mean, there is the majority of producers that actually produce nutrition. While the marine world is largely consuming. So this suggests, that the distribution of land and water on a planet, on a terrestrial planet, is important. The reason why that is so can be seen, from this plot here from Glaser et al. I don't have the time to go into all of the detail, just saying that here photosynthesis and respiration in a balance producing oxygen, we have nitrogen fixation, but most importantly, we have phosphorus being provided by weathering of subaerial weathering of land surfaces. And we can say that nutrition from minerals, the basic of all the nutritions on the planet, is coming mostly from land. There is some submarine mineral weathering, but it is much less effective than the weathering of land surfaces. Also, free oxygen is provided mostly by the burial of organics by land-derived sediments. And the land biosphere, as we've seen in the previous slide, produces much more nutrients than the marine biosphere. So if we would flood everything, we would, provide or lower the base for nutrition on the planet, and therefore the expected production rate and the biomass. And this has been considered by Lingham and Loeb in a paper in 2019, where they looked at the net primary productivity, that is the net rate of organic compounds synthesized by organisms through photosynthesis mostly, and the biomass of producers. And they found that there is a sweet spot about, the land-ocean surface, about, 50-50, like we have on Earth, half land, half ocean surfaces. Actually, on the Earth, it's something like 30% to 70%, but around one. While if you go to ocean worlds covered entirely by ocean planet, then you would be nutrition limited. While on the other hand, if you went to a land planet that is mostly covered by land, you would be water limited. And tectonics would matter here as well, because old cratons, for instance, on the Earth are depleted of nutrients. And also, the topography there is, much less steep than in young mountain belts that can serve as sources for an extended weathering flux. So, in order to provide the nutrition basis, this is good, to have tectonics. And this is one of the reasons why many believe that complex evolved, or maybe life as such, requires active tectonics. I'm, in an older version of that slide, I had plate tectonics there, but I don't think that that is really still necessary. So plate tectonics and other active tectonic modes recycle near-surface rock and volatiles with the planet's interior through subduction. And this would be helping, to generate geologic diversity, like cratons and mountain belts, from continents, land surfaces, with easy access to solar energy and high bioproductivity, recycle weathering depleted surface rock and replenish crucial elements such as carbon, nitrogen, oxygen, phosphorus to sustain the biosphere. We haven't talked about the carbon and silicate cycle, but that is, of course, linked here as well, keeping clement conditions, stabilizing the surface temperature. And efficiently cool the deep interior, and that has popped up here, and the core to generate a magnetic field in the core, protecting the biosphere. Now, I'm coming back to that slide here, but I'm putting one of my slides here in as well. I'm just taking, this cycle of weathering and transport of continental material a little deeper, and saying that through continental erosion and the subduction of continents, you're producing continental rock, and I show that in the next slide. So continental crust is produced, and land surface and land volume is produced by partially melting crust and sediment rock in the presence of water in the subduction zones of plate tectonics. That, at least, the mechanism how the planet works today. It may be have been a little different in the past. This is something that we're still, looking at modeling, but that is what has been, like the planet has worked for the past giga-year or so. The continental surface is eroded by surface weathering and by subduction erosion. So you're taking stuff away from the continents by friction, provided by the subducting oceanic crust. And here you have the mid-oceanic ridges, and there you're releasing water, from the interior. So that is the continental crust cycle. And this is tightly linked to the mantle water cycle. So I just said that you need water in order to provide continental crust, and that water is being processed in the deep water cycle. So we have mantle release of water to the surface, to the water reservoir, but you also have subduction in sedimentary layers, and you feed it back into the mantle. So there's a continuous cycle of water and a continuous cycle of land sediments in that. And that is an important, are two important cycles in how our present Earth works. Now, the long-term water cycle, the importance of that comes to a large part through the effect that water has on mantle material properties. For instance, the melting temperature of the mantle is dependent on the concentration of water. So the more water you have in the rock, the lower is the melting temperature, and the easier it can produce melt and volcanic activity. Also, the viscosity of the mantle, so the viscosity that is, regulating the rate of convection and plate tectonics depends on the concentration of water in the mantle. So the more water you have in there, the lower is the viscosity, and the more effective can convection and plate tectonics actually circulate, and also the production of crust and so forth. So these effects of water on mantle properties is at the heart of our understanding of the working of the planet together with temperature. Now, the crust and water cycles actually are feedback cycles. And here I'm illustrating how you get negative feedback. So let's look at the crust cycle first. So you have increased the crust surface area. Oops. And because you have increased the crust surface area, you have increased the weathering rate. And therefore, you're losing volume of the crust, and you're getting back here. So in a negative feedback. Also, I mean, if you have increased the water concentration in the mantle, you lower the viscosity, you increase the convection speed, and then you lose additional water, at the mid-oceanic ridges, and you get back, to where you came from. So in a negative stabilizing feedback. However, linked to that, and in particular through the combination of the sediments and water being transported in the subduction zone, you also have positive feedback. So increasing the crust surface would increase the weathering rate, would increase the water sediment subduction rate, would increase the melting rate, and would increase the crust volume. Also, if you had increased water concentration, you increase the convection speed, you increase the water that is transported through this crust and sedimentary layer, into the deeper mantle. And so the negative and positive feedback are competing against each other. It depends on basically, the mechanism of this subduction zone, how what is actually dominant. And I'm not going to get into much detail with these equations here, but I just wanted to tell you that this here is an equation that gives you, in terms of the present day, the rate of increase of the continental coverage on the Earth, and that the increase or the rate of change of the water concentration in the mantle, and here's an energy balance. And you see that we have a term here. Now, can I circle that? We have a term here that is proportional to the area of the continents, and that provides positive feedback. And here I have a ruler through this there's this parameter here where I can choose, what should be dominant. Should the positive feedback be dominant over the terms providing actually negative feedback? And also, what's important is that the regassing and the continental production are basically, scaled, of course, as the present water and the present continent, but it's basically the same term. So they're strongly coupled. Now, when we integrate that, so we can choose these parameters here. We have a few more parameters here that parameterize how continents may thermal blanket the mantle, or how heat sources may be distributed. That's not of much importance in our discussion today. But when I have negative feedback mechanisms dominating, that is when this term, here is when Xc1 is relatively small, okay, or Xc1 minus Xc2 is smaller than 0. Then I have a bifurcation here. I'm on the left side of that bifurcation, and I have a stable situation. Now, what's plotted here? Here's the mantle water concentration against the continental fraction. And these lines here are lines of constant continental surface fraction and constant mantle water concentration. So the time rate of change of the surface of the continent is 0, or the time rate of change of water is 0. And when the two cross, you have an attractor. Oops, sorry. And you see that all the arrows are pointing towards that attractor. And the system, whenever it started somewhere, is trying to get to here. On the right-hand side, we see that this is a stable point, so we're going towards that. Now, when I change these parameters here and have them to be larger than 0, then I get beyond the bifurcation, and now I have 3 stable points, or 3 equilibrium points. And the reason why this here bends over is because of the sediment subduction being so effective that I can't increase the continental fraction anymore in equilibrium, by still increasing the water concentration. So I have to go back. And that's a typical S shape in these bifurcation studies. And now I have 3 equilibrium points, one at a small continental fraction, one at a larger continental fraction, and the same spot that I had before. But now this is the saddle point, and the stable points are this one and this one here. If we find the Earth sitting on here, we would, of course, be asking ourselves, how can we keep here? Well, here kinetics comes into the play. You can probably sit here in this place for quite some time. There may be even processes that would stabilize the Earth in here, feedback, for instance, between life and the Earth. So we don't know. But based on the consideration we have so far, we would actually expect us to be here. Now, before I go, let me compare these and put them next to each other. And you see that we have basically the same point, but this time it's a stable point, and this here as a marginally stable point, on a saddle point. These two here are characterized by maximizing the length of continental margins and the subduction zones. So the zones where the continents are produced, while this one here maximizes the crust volume, and this here minimizes crust volume. So this thing here is actually the sweet spot where the planet, is most active, so to speak. So it's maximizing the way plate tectonics works. When I can plot then the mantle potential temperature, mantle water concentration, so solutions to these equations. And you see that when a negative feedback mechanism dominates, that I get an increase first of the continental coverage, and then a decrease towards that attractor. So this would then move as we still cool, and eventually this would go towards here. Now, when I have positive feedback dominating, then I get a continuous increase in continental coverage. I'm not getting the shoot over that I saw in the previous slide, but a continuous increase as we go further in time. And this is due to the effect of the continents on the continental growth rate. Now, how does that compare to what we observe on the Earth? Now, here is a complicated slide that collects all the data that we have on continental growth. I mean, this curve here is actually the present-day surface age distribution. And you see that, we have very little rock, of old age, and mostly is young age. And so it's difficult to reconstruct, how the continents actually grew. So that is one of the boundary conditions. Geochemical considerations, basically inform these curves here, so with a continuous increase in the continental volume. And then, we have Armstrong here, a very old paper, who observed that the water table on Earth was almost constant over the past giga-year or so, and he assumed that the continents formed early and then stayed, like they are. And an even older paper, recognized that effect of continental production and cooling of the Earth that would lead to a shrinking of the continents later in the evolution. And that is actually what is seen when I have that negative feedback dominating. I have this overshoot, and then I move towards the present day. While when positive feedback mechanisms are dominating, then I'm getting basically reproducing what these guys are saying here. And when I look at the cumulative age distribution, this is the positive feedback curve that is pretty much consistent with what we have actually observed, due to the paper by Goodman. And 7% of the continental crust is older than 3 gigayears. This is what we can verify here. Also, the level of the continents above the ocean surface has been constant for the past 500 to 2,500 million years. And this is consistent with a slowly growing continental surface area, compensating the slow decrease or the slowly deepening of the ocean due to the cooling of the planet. So all in all, I mean, this is suggesting that the Earth is actually rather in this configuration rather than that. Now, in a paper in 2019, we have looked at other parameters and also came to the conclusion that the Earth would actually be more in that positive feedback situation. Now, why are the differences between upon cooling between the negative, where you have this overshoot, and the positive, where the continents are slowly increasing? This is basically to do with the evolution of these fixed points here with temperature. So for the negative feedback, you would see that in a cooling manner, see that moving down to smaller continental coverage and water configuration. This is why you have the shrinking continent. While this guy here, upon cooling, stays more or less the same. It increases actually a little bit, goes a little bit towards higher continental coverage. So that is then an explanation for that slowly increasing continents, despite the cooling of the Earth and despite the erosion of the increasing erosion of the continents with continental coverage. Now, the implication, of course, of that is that the Earth is not very likely. And here we looked at a large set of initial conditions and looked at what we would actually get out. And we would find that about the majority, 90% or so of the solutions would end up with a planet that's largely covered by continents. And about 10% or so would be largely covered by oceans. We're not getting here because of kinetic reasons. I mean, here the water concentration gets so small that the planet gets, so sluggish that you are not actually getting there. So that's a kinetic problem, basically. And about 1% or so would be ending there where we find the present Earth. Now, what would be the consequence of that? Now, if everything is is covered, or most of the planet is covered by land, we would actually expect a cold climate, maybe something that the Earth has seen in the Pleistocene, while on the other hand, that ocean planet may be moist and warm. This is a speculation that is backed by our calculations of the surface temperature, in these configurations here. And basically here's the volume out of which we took the initial conditions. And what we see is we need to be on this plane here actually to get to where the Earth is. If we're above that, landing at an ocean planet. If we're below that, we're getting a land planet. Now, what would be the predicted biomass and NPP on that? Now, here is using, again, Lingham and Loeb's calculations. So we would predict that our land planet would have about 40% of the NPP or 60% of the biomass, and the ocean planet a little less than that or a little more. And the difference between here is basically the size of the land factors. So these are not, non-habitable planets. I mean, they can support life, but they just predict, that the NPP and the biomass would be, smaller than we would actually observe it on the Earth. Now, we've assumed plate tectonics. There's a lot of debate going on whether plate tectonics has really been going on for 4.5 billion years. So there may be other forms of tectonics with a more squishy lid, as it has been called in the early evolution. Now, this doesn't really, we're not quite understand it too well, but possibly this doesn't really matter, because what we need actually is this feedback up to continental surface, to the processes in the mantle, and that may not really, depend on the stiffness of the plates. But this is something that needs to be considered. Now, can we actually detect planet surfaces? Well, apparently yes. We could look at the albedo, and the albedo between a land-covered and an ocean-covered planet, could be like a factor of 10. And there was a mission, the EPOXI mission, that tried that on Earth, and could actually reproduce, to some extent, what we observe on Earth. And therefore, I mean, this is a chance that we can look. Well, in conclusion, the land-water ratio matters for the bioproductivity and the biomass. It is thus an important property for a habitable planet. And the role of volatiles in the planetary machinery cannot be emphasized. I mean, it's a very important quantity. The Earth has that favorable land-water ratio, but it may not be a likely outcome even for an Earth-like planet with similar properties, depending on initial conditions. So it would be interesting, if we had 100 Earths, to see, what the statistics actually would be. The sweet spot that we observe on the Earth and maximizes the length of continental margins, and also thus the length of continental shelves, which are important for the production of free energy and the basis for evolved life, animals, biologists, astronomers, planetary scientists, and so forth. It has been estimated by Bertigina and Kuhn that the albedo difference could be like an order of magnitude, and they are pretty optimistic that that could actually be observed, even on exoplanets. Well, so what, as a geoscientist, would I say to astronomers characterizing exoplanets? I mean, characterize your target planet as best as you can. I guess you would do that anyway, but mass, radius, tidal love number for interior modelings, orbit and host stop properties, surface albedo, spectral characteristics, magnetic field, would all be important quantities. But we still, need to improve our understanding of the physics and biochemistry of rocky planets, even the Earth. Diversity, land, ocean, topographic relief, how would that matter? Out of equilibrium, nonlinear processes, nonlinearity of processes, feedback processes, possible feedback between life and the planet systems, things that all need to be explored. And the James Webb Telescope, I'm told, will be able to directly image rocky exoplanets and should perhaps provide us more data. And then, of course, there is other, like the Habitability Observatory or the LIFE, Large Interferometry for exoplanets, on the horizon, things that will, help us get a better understanding of exoplanets and compare with the Earth. And with that, I thank you very much for your attention. And I end with that comparison of land, Earth-like mix, and ocean planet. Thank you.
Thank you, Tilman, for this fascinating talk. Thank you so much. We have a bunch of interesting questions in the chat. If you want to add to the chat, write your questions there, and I will start reading them one by one. So the first is William Wall. How does this analysis change when considering possible life on an ice moon or exomoon with a subsurface ocean?
With a
subsurface ocean.
Yeah. Well, actually, yeah. Like I said, for that ocean planet, you would not expect it to be uninhabitable. But it's just that you could have a biosphere there, and this is for Europa. I mean, you could have erosion at that border at the bottom of the ocean, leaching out phosphorus out of the rock there, and providing nutrients for a biosphere in Europa. But you would not expected to be as produce as much biomass as you would see on Earth. I'm saying here basically that the Earth, is exceptional because it's at a sweet spot, in this regard, and an ice moon or a planet, covered entirely or almost entirely with this ocean, just doesn't have not as good a chance, as producing a biomass, a biosphere as the Earth has. Now, in addition to that, of course, on Europa, you will then also, you cannot use photosynthesis, so you get your energy from chemical reactions and so forth. So, it's different, as you all know, but it doesn't rule out a biosphere. That's not what I'm saying here.
Okay, we have another question now. Sorry, there's a pinging that shouldn't be here. So Ankit Barik, if a low land-water ratio is relatively unfavorable for life, what does that say about life in ocean world?
Well, I would say that you will not expect, the same biomass and bioactivity as you would, for a land ocean planet. Now, of course, I have to say that this is considering, what we know from the Earth. There may be biospheres that are more adapted to ocean worlds, but still, you are limiting your nutrition bases, when you are entirely covered with an ocean. So all you have, is your your weathering of the bottom of the ocean, which is not as effective as subaerial weathering, on the Earth. Yeah, it may still have, but not the same.
Not the same. So we have another question from Santiago Arellano. What would be the smoking gun for detecting active volcanoes on exoplanets? And then a happy 100th anniversary, and thanks for this very interesting from Santiago.
The smoking gun for volcanic activity. That's that is kind of difficult. Of course, if you, depending on the volcanic activity. So, for instance, for Io, you could do remote sensing. Io is so volcanically active that you can actually, see the measure the heat flow from space. Now, on the other extreme, for instance, we have indications in the record of the HRC, the high resolution stereo camera on Mars, for relatively recent volcanic activity on Mars. But the level is so minor, that you can only get that, close to the planet, and therefore, I mean, detecting in a 1 pixel observation, detecting volcanic activity on Mars is basically out. There may be chances of detecting volcanic activity through their effect on chemistry of the atmosphere. For instance, Venus volcanic activity has been constrained by the observation of sulfur and sulfuric compounds in the atmosphere of Venus. So that may be a route to go. Yeah.
Okay, thank you. Nuno Pereira is asking, what percentage of exoplanets are known to have a protective magnetic field against strong stellar and cosmic radiation, potentially allowing life to survive on their surface?
As far as I know, it is not known. I mean, the magnetic field, to prove the existence of the magnetic field directly is pretty difficult. But astronomers are very creative, and I understand that there are ways of constraining the possible existence of a magnetic field. But I don't think that there is a reliable census, so that you could say that there is a certain percentage of so. Also, there is a large debate if you believe, that in order to generate a magnetic field, it is good to have plate tectonics. There's a very lively debate on plate tectonics, on planets as a function of their mass or their radius. I, together with others, have argued that a super-Earth, may not have a magnetic field, but there are others that say that actually they would expect a super-Earth to, be even more likely have a magnetic field that in comparison with the Earth. So that is a matter of very, very lively debate, and that is, basically hampered by our problems of assessing the properties of material in the deep interior of super-Earths. So we do not know at the moment whether a 10 Earth mass super-Earth has really a core that is distinct from the mantle, or whether they are dissolved into each other, and there is a gradual a boundary between the two, and how that would actually affect the production of a magnetic field and so forth. So that is a matter of very lively debate, and that is, why I'm saying that we, still need to get a better understanding of terrestrial planets, even the Earth, but also, more than that, even of planets bigger than the Earth, where high pressure effects come into play.
Thank you. A lot of more interesting questions are appearing. So Mark Vietzerek, what types of geophysical observations do you think we will make over the next decade or two? For example, the existence or not of a magnetic field, you already touched on this, and its strength. What about rotation rate, precession, shape, flattening, moment of inertia, surface temperature, etc.? What's your expectation?
Yeah, hi, Mark. Actually, for you and I, what I think is really fascinating is that we're, getting from the rate of the precession of the orbit of the planets constraints on the tidal love numbers. And that, as I don't have to tell you, would allow us to go beyond the mass, radius, the constraint, and include the moment of inertia calculated from the love number, and that should give us the way forward. Also, surface temperature is something that is being already calculated and derived from the observations of exoplanets. So that is something that one could actually count on. So basically people have a relatively good idea how hot the surface of a planet would be. Also, there is, of course, model dependent to an extent of the rotation and how, well, there's actually ways of constraining the rotation rate of an exoplanet. So that is something that could become better. And then, I'm looking very much forward to seeing what astronomers can actually derive from direct observations using the web. And that will be, could be changing things to quite an extent.
Thank you. So Mustafa Obozugwa Usman is asking, does increased water in the desert leads to increase in life and biomass? Why and why not? And then why do we have hydrocarbon deposits in the desert region like Saudi Arabia with little fossils concentration?
Well, because the desert in Saudi Arabia wasn't always a desert. So that is basically the explanation for that. So what is a desert today, due to continental drift and other factors, and climate change on the Earth, going back, billions of years, has changed the distribution of surface types on the Earth, and therefore you have hydrocarbons in Saudi Arabia because you had vegetation there at previous times, and you profited from it now. But yeah.
So Andrew Lazarevich is asking, what may be, or if there is, the optimal land-ocean surface area ratio for active plate tectonics? Plate tectonics seems likely to be important for our own development on an Earth surface, changing capability, possible detectability of Earth from other worlds.
Yeah, well, from our calculations and what I've tried to show in this talk is we're talking about something like a 50-50 relation. So in our calculation, the sweet spot was at 40% continents versus 60% oceans. That is continental crust versus oceanic crust. And because the continental margins are flooded, I mean the land surface is a little bigger. Now, of course, that depends on parameters, so that sweet spot may change. But also from the calculations of Lingham and Loeb and others, we're talking about half-half, and that's something that seems to be about the sweet spot for that. Now that is, of course, I mean, assuming the Earth as is with its Cialic continental crust and so forth, and assuming that plate tectonics produces that. So it's something I would say for Earth. Now, if you look at Venus, you can of course speculate what happened to Venus. Would Venus be is there in a way? Well, maybe Ishtar Terra is a continent. It is a highland. Most of the surface of Venus seems to be basaltic, but maybe not Ishtar Terra. So Venus, might have been something like, this ocean world that I had water, and there's speculation that in its early evolution, it might have had water. But that is, of course, then extending the model back to the very early times on Venus. And there, of course, we're getting into very uncertain terrain, So, but it's a speculation that one might make.
Thank you. A couple of more questions. So Thierry Momerle is asking about tides and satellites to generate them. What about life if Earth didn't have a moon?
Yeah, that's an interesting question. So it is often said that the moon stabilizes the Earth's rotation rate, and therefore basically the climate distribution on the Earth and the Earth's rotation rate didn't have as wild excursions as the Martian rotation rate, and that this is favorable for development of life on the planet. Now, I personally think that is, probably true. So stability of an environment, is probably positive. But I've increasingly heard, people questioning that and saying that maybe it is not as important as people would have thought for the development of life on this planet. So I think that's an open question, an open debate that is ongoing at the moment.
Okay. One final question from our own Mark Sargent. So Mark says, primitive microbial life developed on Earth quite early, less than a giga year in its history. If we were now also to find evidence of past or current organism on Mars, would this change your conclusions about the importance of geodynamical processes like plate tectonics for the existence of life?
Let me say, and apparently I haven't been too clear about that. I'm not saying that you need plate tectonics for any form of life. I'm pretty sure you can have life, primitive life on a planet like Mars, for instance. So I wouldn't be surprised if, at least for that reason, that if you would find life on Mars, there are other factors that people are putting forward that make Europa a better candidate than Mars, but that's not the discussion at the moment. What I'm saying is, and what I think is pretty much agreed in the community, that for the evolution of life and getting beyond the most primitive life forms, tectonics is a good thing to have, perhaps even necessary. And it is also possible, and one has to think further about that. If you like on the planet Mars, if you don't renew the surface, that the resources may be exhausted at one point in time. But Mars had volcanic activity, and therefore there is some replenishment, but it's all not as effective as you would have it on a plate tectonics like the Earth.
Okay. We have a final comment from Dr. Tem saying we have the great unconformity. Visible life developed 500 to 600 million years ago. It took almost 900 million years to develop life on Earth. It developed because we had plate tectonics. So that was just a comment with an exclamation mark.
I agree.
Agree. So I think with this, we can conclude and express our gratitude and our honor to host Tilman Spohn, the creator of this very successful series, to give the number 100 seminar. And I think we can only wish 100 more equally successful. And we thank you for this fascinating talk. The talk will be posted on YouTube. So for all the people who couldn't finish watching, please tune in there. And thank you, Tilman, again.
Thank you very much, and thank you very much for your patience with me. Getting with me.
Fantastic. And fantastic
And have a
questions.
good evening, day, wherever you are. Okay.
Thank you.